One-dimensional steady-state heat conduction without heat generation through homogeneous and isotropic material having constant thermal conductivity K with reference to temperature. Under this heading, let us discuss heat conduction through composite sphere under combined mode of heat transfer. That is, heat is being transferred both by conduction and convection as well. So like composite cylinder, we have defined composite sphere is a sphere having two or three different layers of materials have been provided over it in order to prevent heat loss from the hot fluid it is storing to the surrounding. So one such composite sphere is shown in figure, whereas the base sphere is provided with two layers of insulating material having thermal conductivity K2, K3. Material 1 is having thermal conductivity K2 and base sphere is having thermal conductivity K1 respectively. This composite sphere is carrying or storing hot fluid inside having its convective heat transfer coefficient H infinity I and temperature T infinity I. The different temperatures at the inner surface of the sphere are T1 at the interface of sphere and insulating material 1 is T2. The temperature at the interface of insulating material 1 and 2 is T3 and temperature of at the outer surface of the sphere is T4 and finally temperature of the cold fluid to which this entire system is exposed is T infinity O. Let's say temperature of the cold fluid like air or cold water is H infinity O and its temperature is T infinity O. Here we are considering hot fluid is inside and cold fluid is outside. So by virtue of this temperature difference, heat will be conducted as well as convected through this system from hot fluid to the cold fluid. Heat will be convected from hot fluid to the inner surface of the sphere. Heat will be conducted across the sphere insulating material 1 and 2 surfaces, and finally heat will be convected from outer surface of the sphere to the cold fluid by convection. So here combined mode of heat transfer is involved. In this sphere, heat can transfer in three directions: radial, tangential, and azimuthal. But we are assuming heat transfer only in radial direction because I am considering one-dimensional steady-state heat transfer. And when heat is being transferred from inner hot fluid to outer cold fluid, temperatures at the various phases will be changing and locus of all those temperatures is called as temperature profile, which happens to be hyperbolic or in case of sphere. Now let us draw the equivalent electrical circuit for heat transfer through this composite sphere. So the flow quantity will be rate of heat transfer. The first potential difference will be temperature difference between hot fluid and inner surface of the sphere at radius r1. And let's say this fluid layer is going to offer thermal resistance by convection RT infinity I. The second potential difference will be in the form of temperature difference T1, T2 between inner surface of the sphere and outer surface. And the material of the sphere will offer some thermal resistance by conduction. Let's say it is RT1. The third is the interface temperature of sphere and insulating material 1. And T3 is the interface temperature of insulating material 1 and insulating material 2. So here the insulating material 1 is going to offer thermal resistance represented by RT2. The fourth potential difference will be in the form of temperature difference T3 and T4, where T3 is the interface temperature between insulating material 1 and 2, and T4 is the outer surface temperature of sphere, and the material of the insulating material 2 is going to offer thermal resistance by conduction represented by RT3, and finally the potential difference will be in the form of temperature difference T4 and T infinity O, and this is the temperature difference between outer surface and cold fluid. So the cold fluid film will offer convective thermal resistance to this heat flow represented by RT infinity O, and finally heat will come out. So as you can see here, there are 3 layers of solid materials and 2 fluid layers. Out of 5 resistances in all, 5 resistances will come into picture in the path of the heat transfer. Out of this 5, 2 resistances will be by convection and these 3 resistances will be by conduction. And let's say radius of this composite wall system are R1, R2, R3 and R4, and rate of heat transfer in the radial direction is Q. In this our entire analysis, I am going to assume no thermal contact resistance. So assumption will be no thermal contact resistance. And assumption number 2 will be no heat transfer in either tangential and radial direction, because we are considering one-dimensional steady-state heat conduction. Now our aim is to find out temperature variation. The aim of the entire analysis is to find out temperature variation and the second aim to calculate the heat transfer rate Q. Now how to achieve these two aims? As we are assuming one-dimensional steady-state heat conduction, under one-dimensional steady state heat conduction, what we can assume, the rate of heat transfer Q is equal to rate of heat transfer from hot fluid represented by I to the inner surface of the sphere is equal to rate of heat transfer from inner surface to the outer surface of the base sphere is equal to rate of heat transfer from outer sphere to the outer surface of insulating material 1 is equal to rate of heat transfer from outer sphere of insulating material 1 to outer sphere of insulating material 2, and finally from outer surface of the insulating material 2 to the cold fluid. So all these of rate of heat transfer will be same. Out of this 5 rate of heat transfer, this will be by convection because it is the heat transfer between fluid and surface. These 3 heat transfer rate will be conduction because they are the heat transfer through solid surfaces. Now let us write down the rate of heat transfer for these individual rate of heat transfer. Let us find out the expression for this individual rate of heat transfer. So this will be by convection. So I can recall Newton's law of cooling and write it as H infinity I AI T infinity I minus T1 excuse me. This is the rate of heat transfer through a spherical wall. So I can write it as 4 pi k T1 minus T2 over 1 over R2 minus, sorry, 1 over R1 minus 1 over R2 will be, and the thermal conductivity will be thermal conductivity of sphere, that is K1. Then Q1 to 2 will be, Q2 to 3 will be 4 pi K2 T2 minus T3 over 1 over R2 minus 1 over R3. Then Q34 will be 4 pi K3 T3 minus T4 over 1 over R3 minus 1 over R4, and finally H infinity outside area into T4 minus T infinity O. So these are the individual rate of heat transfer. Now let us arrange them in the form of temperature difference and thermal resistance. So T infinity I minus T1 over 1 over H infinity I into AI. The second equation will give me T1 minus T2 over 1 over 4 pi K1 1 over R1 minus 1 over R2. The third equation can be written as T2 minus T3 over 1 over 4 pi K2 1 over R2 minus 1 over R3. The fourth equation can be written as T3 minus T4 over 1 over 4 pi K3 1 over R3 minus 1 over R4, and final equation can be written as T in T4 minus T infinity O over 1 over H infinity O into A. This way I can modify the above equations in the form of temperature difference and some denominator parameter. So I can further write these as T infinity I minus T1 R T I. Let me check how did I represent this resistances. Okay, I have represented it by I have to write it RT infinity I is equal to T1 minus T2 over RT1 is equal to T2 minus T3 over RT2 is equal to T3 minus T4 over RT3, and finally T4 minus T infinity O over RT infinity O. Now if I compare these two equations, set of equations, I can get RT infinity I is convective thermal resistance of hot fluid, and it can be given by 1 over H infinity I into AI. I can also write it as 1 over, where AI is the inner surface area of the sphere, so I can write it as 4 pi R1 square into H infinity I, and its unit will be Kelvin per watt. Now RT1 will be conductive thermal resistance, and it is conductive thermal resistance of base sphere, and it can be written as 1 over 4 pi K1 1 over R1 minus 1 over R2 Kelvin per watt. RT2 will be conductive thermal resistance of insulating material 1. So I can give it by the expression 1 over 4 pi K2 1 over R2 minus 1 over R1. RT3 will be conductive thermal resistance of insulating material 2, and it can be given by the expression 1 over 4 pi K3 1 over, sorry, this will be R2 minus R3, extremely sorry, and this will be 1 over R3 minus 1 over R4 Kelvin per watt, and finally RT infinity O is the convective thermal resistance of cold fluid, and it can be represented by 1 over H infinity O into AO, where AO is the surface area, outer surface area, 4 pi R4 square into H infinity O, Kelvin per watt. So this way I can calculate thermal resistances offered by individual layers of fluids and materials. Now if I want to calculate the heat transfer rate, considering the inside hot fluid and outside cold fluid temperature, so I can write in this fashion: T infinity I minus T infinity O. So all the thermal resistances of the material coming in between T infinity I and T infinity O will get add up. So it will be RT infinity I plus RT1 plus RT2 plus RT3 plus RT infinity O. So it can also be written as T infinity I minus T infinity O over summation of RT, where summation of RT is total thermal resistance of the composite sphere. Total thermal resistance of the composite system or composite sphere, I can say, and it can be given by summation of all the thermal resistances in Kelvin per watt. So this way I can calculate total thermal resistance. Now I can also calculate overall heat transfer coefficient, because whenever combined mode of heat transfer comes into picture, overall heat transfer also comes into picture. And we also know for cylinders and for spheres, their inner surface area and outer surface areas will be different. So we can have overall heat transfer coefficient based on inner area So it can be given as Ui into AI over 1 over summation of RT. So from this you can get the expression for UI, and case 2 based on outer area. So it can be given by UO AO is equal to 1 over summation of RT. From here you can get the expression for UO. So let us do for this UI. UI AI is nothing but 1 over H infinity AI plus 1 over 4 pi K1, 1 over R1 minus 1 over R2 plus 1 over 4 pi K2, 1 over R2 minus 1 over R3 plus 1 over 4 pi K3 into 1 over R3 minus R4 plus 1 over H infinity O into AO. So if you multiply this entire expression of thermal resistance by AI and simplify, where AI can be 4 pi R1 square. So I am directly writing the expression, skipping 2-3 simplified steps. So the first term can be written as H infinity I, as AI will get cancelled by this. If I write AI here, 4 pi will get cancelled and I will get R1 square over A1 into 1 over R1 minus 1 over R2 plus R1 square over A2 into 1 over R2 minus 1 over R3, then R1 square over A3, 1 over R3 minus 1 over R4, and finally here I will get the ratio of R1 square over R2 square into 1 over H infinity. So this way you will get the expression for Uy, and its unit will be in watt per meter square Kelvin. Similarly, you can find out for UO, which I am not going to derive. So with this, I come to an end of this lecture.